Hello everyone, welcome to this tutorial. My name is Emerson Ahrari, I'm a Google Earth Engine developer. In this tutorial, I'm gonna show you how to calculate the cyanobacteria concentration over the water body using monthly Sentinel-2 images. So here is my YouTube channel. There you can find over 150 tutorials, applicable tutorials about the Earth Engine and its application in the earth sciences. So if you want to learn how to do this procedure, you can find this tutorial on my YouTube channel and I will show you how to do it from the scratch. Okay, let's get started. In the first step, I'm gonna go to the code editor environment, or I'm gonna actually go to the Colab environment and show you how to make a connection between Earth Engine and Colab, because I wanna do programming in the Earth Engine using Python API programming. That's really important thing for us. So, as you can see, after creating a new notebook in the Colab, we need to import essential libraries that are necessary to work with the Earth Engine here. Start with EE library and GEE map, just like this. These are essential ones. However, we need more libraries like Xarray structure or Xarray library. The Xarray structure is very useful because allow us to manage the satellite data in the Python programming without any challenge. So, and another library, XEE, is also necessary because thanks to the XEE, we can actually convert Google Earth Engine image collection into array format structure. So let's run the first cell and we are waiting to uh, until the library is imported or installed. If you face with any challenge during this tutorial, you can find this code example on my YouTube channel below this video in the description box. After importing process done and you saw the successfully installed, you can clear the outputs just like this. Make a new cell, and now we need to establish a connection between Earth Engine and Colab using EE library. EE already imported. So start with authentication first and then initialize your account. The account project ID is the first argument. Go to the code editor environment, code.earthengine.google.com. Upper right, you can find your account information through the project info. Every one of you has a unique cloud project ID. For example, this is mine. As you can see here, my project ID added. Another argument is the OPT URL. If you search on the net about the XEE library, there you can find a GitHub page this address, including a detailed instruction about XEE library. So the XEE library recently developed by the Google developers and allowing us to convert an image collection into Xarray format. If you scroll down a bit here, the OPT URL is available here. Just copy and paste into your code. Something's wrong here. The authentication is not like that. So now the problem fixed and Colab asking permission to get access to your Earth Engine account. Click on allow and now select the account. Click on continue and continue again. Just like this. It's very easy to do and it's very simple. I want to show you how to use the Earth Engine with the simplest code without any challenge. So, make another cell. Before further processing, we need to identify the region of interest. Remember that once we connected to the Earth Engine, we can use the Earth Engine data catalog and capabilities in the Colab environments. So, let's create a new variable map. From GEE map, let's call the map function with a satellite base map. Run the map again, and here you can see we have a user interface with a satellite background, allowing us to select the region of interest using drawing tools available here. So as you can see, if I scroll down a bit or actually zoom in on different areas, you can find several lakes in everywhere in all around the world. So in this tutorial, I'm going to show you how to calculate the cyanobacteria for the water bodies. So it's important to find a water body for your study. So I'm originally Iranian and I prefer to select an area, a water body in my own country. In the southwest of Iran, there is a reservoir here, and here you can see there is a dam and reservoir here, and I want to calculate the cyanobacteria for this area and see how actually these parameters dynamically change through the time, especially and temporally. Through the drawing tools, easily you can find the region of interest and select, just like this. And no matter which area is selected, you can choose your own area. This tutorial extendable to all around the world, not limited to a single places. The platform, dataset, and everything is free of charge and publicly available in the global scale. So, the rectangle created a variable ROI. I made a variable ROI from map select the last feature, convert it into a geometry. Let's run the ROI again. As you can see, now we have the rectangle as a ROI in the code. So in the next step, I'm going to call the Sentinel-2 imagery and calculate the cyanobacteria. A new variable created, Sentinel-2. In the Google Earth Engine data catalog, you can find the Sentinel-2 multispectral product level 2A. The level 2A or SR means atmospherically corrected, and that's the best option for the spectral indices calculation because the atmospheric impact already removed from this data. This data set available since 2017 with weekly frequency. And here you can see the bands and the rest of the information here. First, we need to copy the collection ID and paste it into the code. Then we need to define spatiotemporal filters to actually limit our data set to the region of interest and the temporal period we want to study. Through the dot filter date, I can select the period of time I want to study. For example, I want to study on 2024. I'm going to actually monitor the cyanobacteria variations in 2024. So 2025, but 25 not included. So another thing is another filter is filter bounds. I'm gonna call all Sentinel-2 images for 2024 limited to my region of interest, not the rest of the area. So I'm calling all the satellite data covering my own region of interest. So let's run the Sentinel-2 and check what do we have. The code is running, and after a few moments you can see the results. So 292 images returned. We have an image collection structure. There are some properties and features. If you drop down the features, you can see each feature separately. Each feature including 26 elements, but only 13 bands are available. The rest of things are complementary information for the data analysis. But the main band for the calculation beginning with B1 and ends to B12. The rest of things are for pre-processing or the extra analysis. So as you can see here, each image including this information, and here we have some properties including complementary information about the satellite data, data acquisition, amount of the cloud cover, etc. So now I'm gonna actually call or make a link between Sentinel-2 and cloud probability bands. Here Google developed Sentinel-2 cloud probability dataset, and this dataset is really helpful, and we can join it to the Sentinel-2 for every date, and then we can get rid of the cloudy pixels easily without any challenge. So now I'm gonna make a link between these two kind of collection. That's link collection. The cloud probability collection ID available here. Just copy and paste and enter the probability band. There is a one single band that is probability ranges from 0 to 100. The probability band shows the probability of the cloud cover in each pixel. For example, if a pixel actually shows number 10, meaning that 10% uh, the cloud probability is about the 10%. The higher values, higher cloud cover, lower values, lower cloud cover. So I'm going to show you how to deal with this band. So now I'm going to make a collection between Sentinel-2 and probability bands. And also once we done this process, we will have a new data. We will have a new band as probability in our data set. Let's run the cell again and see what happened. Again, 292 elements returning. If you drop down the features here, you can see still we have several bands here, but this time the probability is also added to each dataset. Okay, now in the next step, I'm gonna show you how to get rid of the cloud cover by the probability band, how to calculate the water body, and how to get rid of the non-water pixels, and how to calculate the cyanobacteria. To do this multi-step processing, we need to make a function that is applicable to over 200 images. So, creating a function begins with the DEF in the Earth engine. So, the DEF, the function name could be, for example, cyanoindex, each input considered as IMG. And when we say each input means that each feature that actually consider it as an IMG, and for each feature we have all of these bands for the processing. So IMG, and here first of all I'm gonna select the cloud band. From input image, select the probability band. Just like this. And cloud free pixels. For example, I'm considering pixels less than 20 as a cloud free pixels. So from cloud image, select those pixels in which their values is less than 20, meaning that the probability of the cloud cover is less than 20%. So I'm considering this threshold as a cloud free pixels, and I want to get rid of, and also by this condition I'm actually removing the rest of the pixels and only keeping the pixels with less than 20 cloud cover probability. So, and the next step is calculate the NDWI, because I'm gonna actually select the water body using NDWI. So first of all, go to the Sentinel-2 data information. If you go to the bands, you can see all the main spectral bands begins with B, and the rest of things is variable, and the rest of the name changing. So here call the surface reflectance bands. From input IMG, select all the bands starting with B. As I mentioned, begins with B, and the rest it doesn't matter. Just select the bands starting with B, because these are the main ones. Then there is a scale factor should be applied before further processing. So copy the scale factor and multiply just like this. Multiply to the value. There you go. So, and as you can see, the surface reflectance created. And now I need to calculate the water body index, normalized difference water index, NDWI. NDWI sets to get the surface reflectance bands and calculate the normalized relationship between band green and band near infrared. Band number 3 here, as you can see, is a green area in the spectral region, and band number 8 is the near infrared. Both of them selected, renamed to NDWI, just like this. And the next thing is the water body. NDWI calculated, and I need to select the water body using this index. In the NDWI, pixels greater than 0.1 showing the water body. And this condition actually removes the non-water pixel. Okay, now we have the cloud-free pixels and we have only water pixels. In the next step, I'm going to calculate the cyanobacteria and then exclude the non-water and cloudy pixels from the cyanobacteria. How to calculate the cyanobacteria? Call the surface reflectance bands, because we want to use these bands for the calculation. Use the expression to write the equation. So now there is a reference for the cyanobacteria, and here in the Copernicus website you can find this article. In this address you can see the paper characteristic, and easily you can go to this website and find the extra information about this satellite, about this index. So if you scroll down a bit, in the session 2 you can find the cyanobacteria equation. This is an experimental model, and here we can use it to calculate for Sentinel-2 imagery. So as you can see, there are some bands, for example, here mentioned based on the wavelengths. And the first thing is figuring out what these actually wavelengths means. As you know, in the remote sensing, each image or each band covering a portion of electromagnetic spectrum. For example, here, when you see in the equation mentioned 516 nanometer, meaning that you need to go to the satellite data characteristic, for example, Sentinel-2, and see or find which one of the bands has closest wavelengths to 516 nanometer. So go to the Sentinel-2 band characteristic, and here wavelengths also mentioned. For example, 516 nanometer in the Sentinel-2 is band number 3, or green band. So now here I'm start to write an equation. In the expression, thanks to the expression, you can write the equation. It's a little bit complicated. The normalized difference is very simple and it's already available as a function, but for the rest of the equation, same as what we have here, we no longer use the normalized difference structure. So that's why I'm using the expression to write the equation. So just type the numbers 115530. These coefficients already extracted by experimental modeling. So that's why actually we can use it for our own study area. So multiply the number, the coefficient multiplies to another actually relationship. There is a division here. We have denominator and numerator. So numerator and denominator. As you can see, 560. So we can make a parenthesis for whole of the division, and the division powers to 2.38, just like this. And the division, we have a numerator and denominator. The numerator 560 is band number 3. That multiplies to the second band is 620. Again, go to the Sentinel 620. Okay, the closest band to 620 here is band number 4. So multiply to band number 4, just like this. Again, in the article, in the denominator, 490 is actually another band. 490, the closest band is band number 2. So over band number 2. Okay, now we have the equation. The equation is written completely, but there are we have some unknowns. B3, B4, B2 are unknowns. So we need to define them. Make a curved bracket just like this and define the unknowns. For example, band number 2, from surface reflectance, select band number 2. The B3 sets to SR from surface reflectance, band 3 considered for B3. And remember to use the comma here. So as you can see, we have to use the comma. And the next one is band number 4. From SR, select band number 4, just like this. So rename the cyanobacteria just like this. The function finally return the cyanobacteria only for the water body by removing the non-water pixels, update mask water, and only for clear pixels by update mask through the clot free, just like this. The clot free and water. So we have the cyanobacteria only for water and clot free pixels. So, and remember that we have some properties for the input image, that's some of them necessary for the output, specifically the system time start, showing the date acquisition for each image. So now back to the code here, and remember to do the copy properties. From input image, take the system time start and add to the output, just like this. Okay, the function, the multi-step processing, now is ready. We need to apply this process on each data set in the Sentinel-2. The map allows us to make a loop structure and apply cyanobacteria or cyanoindex. Let's run the cell. After a few moments, again, you have 292 elements. Go to the feature, and this time only one band is available, the cyano band with the system time start. Okay, we did very well, and everything is ready for the next step. In the next step, I'm going to show you how to use the XEE and Xarray to convert this dataset into multidimensional array structure. And in the XEE environment or in the array structure, then we can use the Python capabilities for the data analysis. For now here, we are doing programming in the Earth Engine, and everything I have written was based on Earth Engine capabilities, not based on the Python capabilities. So, but from now on, I can go to the Python environment or come out from the Earth Engine. So, for example, here I'm making a new variable, a ds, and from Xarray or from the XR library, I'm gonna call open dataset. So my dataset is Sentinel-2 already processed in the Earth Engine. So engine sets to the EE CRS EPSG 4326. As you can see here, the EPSG 4326 is a coordinate system that you can use. Is actually WGS84 coordinate system that is same for all around the world. So you can use it for your own region. So the scale or pixel size here is based on the degree. 1 degree is 100 kilometer roughly, and also zero point 0.1 10 kilometer, 0.001 is 1 kilometer. I prefer 100 meter in this tutorial because for the water body, to my experience, for the reservoirs and water bodies, 100 meter is actually fine. And also most of the time we don't need very high spatial detail because the water body is actually the homogeneous area, and there is no actually variety over the water body. So most of the time 100 meter is fine, because when you increase the spatial resolution, for example, to 10 meter or 30 meter, only the size of the data set increases, but there is no big differences between the outputs. And that's help us to actually make our code more efficient and allowing us to apply more steps on the data set without, for example, crashing the system, without crashing the memory or something like that. The dataset limited to the region of interest. Okay, let's run the dataset, and after a few moments you can see what do we have. So the dataset is ready. Here we had image collection structure, and you saw how image collection looks like. So but now I'm gonna show you how to work with the Xarray structure. As you can see, now our dataset converted into the multidimensional array structure. Instead of a band, we have a variable. Its data available through the time, longitude, and latitude. This is a multidimensional data structure, and there are 292 elements, and here we have 292 actually the values through the time and over the region of interest. Okay, now the data set is ready, but when you bring the data set from image collection, or when you convert an image collection into an X-ray, to my experience, it is necessary to sort it based on a time and then multiply to, in the next step, to multiply, sorry, let me to correct the sort by. First, it is important to sort it based on a time like this and multiply to 1. Scientifically, nothing happens when you multiply your data set to 1, but actually, to my experience, it highly increases the speed of processing in the next step. That's why I'm suggesting to do this multiplication. I don't know why. It's kind of actually, it is not a scientific method. It's completely unscientific, but it's a kind of trick in the Colab and Earth engine. And I found that when you apply a multiply to 1, that actually make a new data set separate apart from the existing data sets, that can help us to increase the speed of processing. Maybe this step takes a little bit longer compared to the rest of the code, but as soon as this part is done, then you can actually run the rest of the code with a higher speed and very easy. So you can see the data set now is ready. In the first step, I'm gonna convert it into the monthly format using Python libraries and Python abilities. So the DS monthly, for example, a new variable, the DS monthly sets to get the DS data set and resample to the monthly frequency. I'm gonna get the average of each month through the time. If you print the monthly version, you can see how data looks like. Instead of 100 or more than 200 images, only 12 array is available. So because we have a monthly format, and if you drop down the time here, you can see we have a monthly dynamic values. So let's do the visualization in the next step. Call the DS monthly again. Select the variable that is cyano and make a plot. The plot has different axes. The x-axis sets to the longitude dimension, as you can see. So the y-axis sets to the latitude dimension. The call axis sets to the time, because I want to have a multi-temporal plot that shows the cyanobacteria dynamics over the time and over the location. So, and the time explaining the temporal variation. The next is the CMAP. The color palette could be rainbow. Robust should be true to avoid outlier impact on the quality of output. It highly increases the contrast. Okay. Oh, just let me to just a moment. I need to add a call wrap also, because as you can see, we have a multi-temporal map, and I need to actually set how many image I want to have per row. I set call wrap to 6, and now you can see the cyanobacteria dynamic looks like much better, and you can see its variation through the time. Okay, and you can see actually how it looks like through the time and the range of the values. The higher values, higher concentration, and the lower values, lower concentration here. And even you can see most of the values are below, for example, 400 or 300. We can actually increase the contrast by setting Vmax to 300, for example. It's totally up to you how to do the visualization. Now, when you actually doing some sort of stretching technique, it can increase the contrast and it is easier for the interpretation. Or even we can decrease it to 200, the maximum value. When we actually do such kind of contrast, that allows us to see the concentration in the rest of the dates. So as you can see in the 2024, in the May, we have very high concentration of the cyanobacteria, and also, but it's dynamically varies from one time to another time. So if you want to save this figure, before to save this figure, we need to actually import the pyplot matplotlib matplotlib.pyplot as plt. The matplotlib is essential libraries to deal with the plots in the Python. So now from plt, let's call the save fig, save this figure, and the figure name is, for example, Sentinel-2 Cyanobacteria with PNG format, DPI 360 BB box inches, sets to the type, and let's run. After a few moments, in the left panel, you will have a shortcut. There you go, you can see the Cyanobacteria Sentinel-2. Let's open and save. So you can see there is Cyanobacteria Sentinel-2 is also available, and you have a high quality output that shows the cyanobacteria dynamic over your region of interest. So in the next step, I'm going to show you how to make a graph that shows the concentration average through the time. So maybe sometimes only the average for whole of the area is important, and maybe we don't need to have more detailed spatial information. Only the temporal dynamic is matter. Sometimes that works like this. So now I'm gonna get the average through the time. Calculate the average over longitude and latitude. So, and let's print the ds_min. As you can see here, we have one average through the time. So now we can convert it into a data frame. It is easier to work in the data frame structure to data frame because we only have two values, one date and one average value. That's two data frame. Just like this, you can have a data frame including the cyanobacteria. But remember that we want to do this for the monthly data set. I forgot to do it for the monthly. The monthly mean, ds_min to the data frame. Now you can see the monthly variation over the time. So, and if you want to save, we can actually save it as a CSV file, df.2csv. This is cyanobacteria. Sentinel-2 Cyanobacteria. .csv format. Let's run. Go to the left panel. The CSV file is also available. You can download and open it up into Excel file. So, or if you do the double click here, you can have this table also as a preview in the right panel. There you go. And even we can make a plot here, very easy, called the data frame, make a plot, just like this. The plot could have a marker like this, and we can actually change the figure size, for example 7.2 or 7.3. There you go, and shows the cyanobacteria from one day to another day. Through the multi-temporal, through this graph, you can see the highest concentration belongs to the May, and since then the amount of bacteria decreasing through the time, and you can see ups and down easily without any challenge. And you can even save this figure by plt.savefig Sentinel-2 Cyanobacteria graph with PNG format, BB box inches tight, and let's see what else. DPI sets to 360. Let's run. In the left panel, the PNG file is also available. Easily download in your system. Okay, and you can see how actually the target results created, and we made nice output for our work. Okay, I hope you like this tutorial, and I'm asking you to share this tutorial with all of the users interested to learn about the Earth engine and remote sensing. I hope you like it as much as I did. Thank you for your attention.